Okay, I want to apologize for the noise problem near the last of the first video on the new diode electrolysis. I moved the camera too close to the beaker, and we all know what happens when we do that. This cell is now established, and it's running 12 volts, 28 milliamps, about 300 milliwatts. You can see that white LED. And I'll move in and show you gas, but at this point I want to show you the spectrum. I think that's of more interest at this point. So what I've done is I have a small antenna that I use for a pickup of the SEC exciter, and here's the spectrum, and this is all going to start making sense eventually here. What I have here is 100 megahertz bandwidth. 50 megahertz would be the center frequency, or the center mark right here. And if you look, I have my marker placed right here at the top of the primary frequency. That marker, as close as we can resolve it with this bandwidth, is 13.8 megahertz. So let me move this marker out now to the third harmonic, which is right there, and that resolves to the best we can get it right here as far as the number of digits is 41.5. So remember 13.8 and 41.5. If you know what the natural frequency is and how I calculate that, this is the natural frequency right here, the one that's reading 13.8. That's at 13.750.205. So there's your spectrum. Now, yes, indeed, it does go out farther than that. Let me go ahead here for a second. I'll increase the bandwidth to 200 megahertz and set the center at 100, and you can see what happens there. Okay, here I've expanded it out now to 200 megahertz, with 100 megahertz being in the center. This right here is the FM band, as well as spikes coming out of the SEC exciter. Now you can see here is what we were looking at in the beginning, this first 100 megahertz, and you can see there's a large spike right here which was past the 100 that I had for the initial bandwidth. And what we see here now is some additional harmonics all the way up to the 200 megahertz mark, and actually we have harmonics that will stretch out to probably around 475, and they're all spaced at ZC. So, well, I'm sure that if you've been following my work, all of this makes sense to you now. But let's go back to this diode electrolysis. We'll return to the spectrum here in a few minutes. Okay, I thought I'd give you a quick shot here of the cell. And if you see the ferrite bead at the top, that's the one where we're getting the gas liberation from. You can see it quite nicely. You can also see the bubbles cracking the surface around the ferrite bead and the ones that are adhering to it. Now, one thing that I better bring into vogue at this point, let me move this out of the way, is don't think you're going to accomplish anything better here by changing the structure of the electrodes that are doing the electrolysis. Here, for example, is a small tuning capacitor, air tuner, and I actually tried using this in the experimentation when we started out as a set of plates, and when that's fully meshed you can see the actual distance between them is very small and even opened up, but it will not work. If you start sticking in large electrodes, you're going to stop the electrolysis and the whole action will end. The way this would normally be configured is you can see that you can easily separate any gas from each electrode by placing, for example, a plastic tube around the ferrite bead and putting all of those into a manifold and collecting the oxygen and the hydrogen that's being liberated separately. So this is a very easy way to capture that gas and separate it. You cannot go to a conventional plate mechanism by increasing the actual area and thinking you're going to pump more charge through it and get more gas. That doesn't happen. Actually, the smaller the liberation area, the better this whole system works. Okay, so let me go ahead and move on. We're up at 5 minutes on this tape already, and I want to go ahead and change this a bit and show you something else. Let me turn this light out here, get that out of the way. Take a look at this power supply. We're 12 volts, 28 milliamps. Now we say, okay, well, we're producing a tiny bit of gas and we've got one white lead, which isn't too bad. A scenario for something as simple as this would be a solar cell charging a battery, and you run the battery and produce cooking gas, and you have some light while you're doing it. This would be during the day you'd charge the battery, at night you'd get your cooking gas and have some light. Well, here, let's take and try to improve the electrolysis here a minute. Let me go ahead and hook something up and then I'll show you what it was. Okay, now I'm probably going to mess up my audio here, but I will release it and get back away from it so that it doesn't happen. Here's another L3. Again, some turns removed, so we're operating at the same frequency. I'm just going to stick one end. One end's open. I'm going to stick one end. Makes no difference which side of the LED or capacitor you hook it to, but watch the LED when I hook this thing up and stick it on there. Look at that. It increased in intensity again, didn't it? By just the addition of that coil hanging there. And we are also increasing the amount of gas production, which now, without the aid of the magnifier, whoops. Okay, I hope the sound wasn't messed up there, but without increasing the current, which we're now running 12 milliamps, we have decreased current, we have increased light output, and we have increased electrolysis. Okay, so we say, well, that's great, but can we do anything different? Of course we can. Let me go ahead and make another change. Okay, now we're going to see something that resembles a somewhat normal way of reacting. We're at 8 mils, 12 volts, and here's a 12 lead panel with a modified L3 again. And of course we're still doing electrolysis. So before, where I just had the coil hooked to it, let me go ahead and hook that coil to it. And did you see what happened? And also, look at the 12 LEDs. Now, this is a little bit different. We're back to 26 mils again. Okay, which is still fine. And surprisingly enough, look at what's going on with the gas. We are liberating far more energy in hydrogen. Look at that. Look at the difference between that and when we take and disconnect our additional lighting. Look. I mean, that obviously says, wow, that's neat. The more things we tie on here and the more energy we use, seems like the more energy we're going to produce, doesn't it? And so it's obvious that even though we're doing this in the conventional SEC one wire scenario, one wire through this modified L3 into this 12 LED board, with the two electrodes immersed in the water that is being electrolyzed, the two 4148s, the white LED here, the small capacitor, and the exciter itself, we're doing all of this for 26 milliamps at 12 volts. Now, as I've said before, we can scale this up further and further. Now, obviously, we're not going to be laying L3s out here and more light boards. I'm going to show you a way where we can take and actually obtain that additional light right here within the same circuit. And what's going to be very significant is every time we draw more out of this beaker or more of the charge out of the beaker into a load and back into the beaker, the better it all works. So let me show you the spectrum one more time. Okay, so let me zoom in here. I've got it set back with a bandwidth of 100 megahertz, center of 50 megahertz. Here, right up here behind the display is my marker, and that's set at, oops, sorry, trying to do this one-handed, how silly, 13.8. Remember that, and we'll go back to our cell. So okay, I think that's enough. We're 10 minutes 57 seconds into this one. We'll go ahead and move on to a third one. I may not get that done today on Sunday, but I assure you I'll try it on Monday if that's going to be a hold-up for it.